Hello everyone, welcome to this session. My name is Shubhadeep. I am the CEO co-founder of Valtrix. We are an EDA company developing solutions for functional verification of CPU and SoC implementations. Today I am going to be talking about the different mechanisms and methodologies employed in Sting to ensure the functional correctness of RISC-V vector and bit manipulation extensions. These are the latest additions to the RISC-V specification to support complex arithmetic operations which are required for a wide number of use cases such as AI/ML and deep learning. Today's session is divided into a number of topics. I'll start with a quick status of where we are with respect to the support for these extensions, followed by a brief overview of Sting. Then I'll be talking about the verification strategy, results in terms of bugs found, and future work. So currently we are working with the version 1.0 draft of vector and version 0.93 of bit manipulation specification. These are used as reference for all our tool and test development activities. All the instructions developed by both the specifications are fully covered now. And like the specifications, the enhancement to the Sting tool and the tests are also a continuous work in progress. Before we start, I would like to give a quick overview of Sting. Sting is a highly versatile design verification tool developed by us at Valtrix for RISC-V based systems. It generates highly configurable and flexible bare metal programs which consist of intelligent self-checking sequences for the design and the test. The tool supports different flavors of constrained random, directed, and graph-based test generation methodologies, and the stimulus generated is fully portable across all the verification environment. Sting also supports a very powerful test stimulus development framework for RISC-V. The framework provides a number of features which enables our users to write tests for custom extensions and microarchitectural features with great ease. The tests are parsed, processed by Sting, and rendered into the final test. This integration with the natively generated test, which include different stimulus patterns, leads to a much increased cross-product coverage. In this slide, we will cover the verification strategy of Sting for these extensions. All the test scenarios were derived from a test plan developed by Valtrix. Pattern-based tests were developed to check functional correctness of the instructions. Support for the vector and bit manipulation instructions were then added to the constrained random and graph-based test generators of Sting for testing interoperability with other instruction classes. The programming framework was also enhanced to meet the requirements of the directed scenarios defined in the specification. Lastly, a lot of existing tests were modified to test cross-products with use cases of physical memory protection, privileged execution, and virtual memory. Fixed pattern directed tests were created early in the development phase. They involved defining datasets of fixed input and output patterns for every instruction. Interesting corner case values are covered in the datasets, and it was pretty useful for basic testing of the ISA implementations. Once the datasets are ready, snippets were developed to program the input patterns and execute the instruction. The results from the execution were then checkpointed and compared with the expected output, and an error was reported in case the failure was detected during the comparison. In case of vectors, the datasets were also tested with different configuration settings which included the supported SEW and LML values, different combinations of the CSRs and the mask registers. Since the number of combinations were huge, the vector datasets focused only on the pure combinations supported by the implementation. Since fixed pattern tests were not sufficient to test all input and output values, we also developed random pattern tests, where the source registers were programmed with randomly selected values. The expected output was then simulated by Sting and compared with the result obtained from the DUT. In case a mismatch was detected in the comparison, the test would report an error and exit out. Although pattern-based tests are useful in the initial phases of design, they tend to add a lot of unwanted instructions in the test. Once these pattern-based tests are path cleared, the focus shifted to constrained random and graph-based test generation for increased cross-product coverage. The correctness of the random test was ensured by a host of checking mechanisms supported in Sting. One of them involves checking the results of the test against a functionally accurate model. We at Valtrex have been using RISC-V OVP sim for co-sim checking the results of our vector tests. It is a RISC-V reference model developed by the team at Imperas and is available for free and commercial use. After the support was added into the random test generation, more than 35,000 configurations were developed to test different biased random sequences of vector and bit manipulation instructions. The other area which required considerable focus was to make sure that the implementation is compliant with the different scenarios defined in the specification. The snippet programming framework was enhanced to meet the directed testing requirement of vectors. Allocation construct for vector register, cases for illegal stimulus, and a number of other things were defined and added. Snippets were also leveraged to provide cross-product coverage with existing scenarios for protection, virtual memory, and cover the different pipeline dependencies for the vector and bit manipulation instructions. In terms of results, we have found a number of bugs of varying complexity in all the implementations we have tested so far. There were several bugs in the area of incorrect instruction decodes, instruction logic, and compliance with conditions present in specification. There is plenty of work still remaining. As the specification is still evolving, it requires us to continuously monitor the changes and modify the tests as required. There are also a number of areas which are not defined very well at this moment. We'll be adding support for those when they get ratified. Also, we are working on the Sting Coverage Manager utility to check how well the test plan is getting covered and take feedback from it to fill up the coverage holes. So that's all for today's session. I hope you found it useful. In case you need more information, feel free to visit our website or write to us. Thanks a lot.